Okay, everybody, how are we doing? So today we're starting a new chapter all about graph theory. So this is supposed to be a little bit more fun, and it's definitely more fun than what we were doing last time with logic, okay? So a little bit more fun on this one, lots of drawing here. Okay, so this first section we're looking at is called Euler Circuits and Hamiltonian Cycles. And I know that looks like Euler, but it's Euler, that's the way you say his name, Euler Circuits and Hamiltonian Cycles. And you guys have all seen this before someplace, but you just never heard proper names for it. So I'm going to give you a little example to start with. Okay, so I'm going to draw you a little picture. Okay, so we've got basically like a house with a cross through it, right? And the question is, can you trace all the lines without picking up your pencil? Okay, and so sometimes you see these like, like on certain web pages, you might see them up above and it says, can you sketch this? If you can, you might be a genius, blah, 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 different things like that. So this is a practical problem though. Can you trace all the lines without picking up your pencil? Okay, so you got to go through all of the lines, all the points, and not pick up your pen or pencil. So, I mean, you could basically start anywhere and you could kind of give it a go. Like, let's say you wanted to start here, and let's say you went up and then down, down, over, up. Okay, but then we get stuck here. Okay, so there's no retracing. Okay, make a note of that. No retracing. No retracing. Okay, so that doesn't work. All right. So you could sit here and you could fiddle with this for quite a while trying to figure out if you can do this or not. But once we understand the ideas behind this problem, just drop again there, I can tell you that yes, you can trace this one without picking up your pencil or retracing. And if you start here, it's that quick, okay? So you could sit here with this one, and if you started at any of these other points, you could sit here for a long time trying to make this happen. But if you start at this point down here or at this point over here, everything works and it works easily, okay? So we gotta figure out what the deal is, what's special that you can do it from some points, but you can't do it from other points. But before we get to that, let's name this instead of having to write this down over and over and over again. So this is called traversable. So put it right here. Traversable. So we say a graph. They call, it doesn't look like a graph, but that's what they call this here. So a picture or a graph. We say a graph is traversable if we can trace each line segment only one time. Actually, I guess we should say all line segments, so we can trace all line segments only one time. Okay, so every single line segment gets traced, and it's only traced one time. So instead of having to write this sentence now or this question over and over again, I can just say, is this traversable? So in this case, this guy is traversable. Now, again, it didn't work the first time I tried it, and it maybe didn't work the second time you tried it or whatever, but eventually we found a place to start where it works. So let's look at this. I'm going to get rid of all my scratchings around it and just redraw it again. Right, there it is. look at this and decide why if we started here, it didn't work, but if we start here, it does work, okay? So what I want you to do is think about each point or where the line segments come together as like a vertex or vertices. Okay, so these are going to be vertices. And when you look at each vertex, you want to note how many lines are coming out of it. So notice how at this vertex here we've got 1, 2, 3, 4. This vertex here we've got 1, 2. This one we have 1, 2, 3, 4. This one we have 1, 2, 3, 4. Okay. This one down here though we have 1, 2, 3. And this one over here similarly we have 3. Okay, so there are 3 lines coming out of these 2 vertices on the bottom, and that's our key. Okay, that's our key. The fact that there are 3, which is an odd number, okay, is what makes this traversable, but meaning that we have to start at that odd, we call that an odd vertex. So we had to start at either this vertex or this vertex. And the thing is notice, as we traced it, we started here and we ended up at the other odd. So we can say, let's see, what notes here. A figure is traversable if it has 0 or 2 odd vertices. Okay. So we'll get to the 0 in a minute. Okay, that's even more special, but right now we've got these 2 odd vertices. So we had an odd vertex here and an odd vertex there, and we were able to trace. Okay, now if we had more than 2 odd vertices, we would not be able to do this. So let's see if I'm gonna put some points here. It doesn't really matter what this shape is that I'm going with here, okay? So let's see. Okay, whatever, we just needed a shape. Okay, so we look at this guy and we ask ourselves if this one is traversable. Now, instead of getting out my purple pen and sketching all over it, instead what we're gonna do is we're gonna count the vertices. So here we've got 1, 2, that's an even vertice, and this one has 3. So here is an odd vertice. 1, 2, 3. This one is also an odd vertice. Now, in order for this to be traversable, we can only have 2. So if we have any more odd vertices, there's no way this can happen. So we come down to this one, and 1, 2, 3, uh-oh, there's another odd. Now, you don't need to try to do anything else in this problem. We already know that there's no way it can be traversable. So not traversable, because it has more than 2 odd vertices. So the idea is that you have to start at one of the odds and you will end at the other. But if you have more than 1 or more than 2 odds, life throws you a trick. And I'm serious, you could sit here and you can sketch all day long. You can go down, up, over, dang it, we're stuck. I mean, so you get stuck right away. So 2 odd vertices is what we're looking at. Okay. All right, now, as we said here, when we have these 2 odd vertices, you start at an odd and you end at an odd. Okay? Start at an odd and end at an odd. Start at an odd vertex, end at the other odd vertex. Okay, so traversable. All right, now let's take it one more step and make it even a little bit more special and call it an Euler circuit. So this guy here is traversable, but it is not an Euler circuit. What an Euler circuit requires is it requires it to be traversable, but it also requires it to start and end at the same point. So, an Euler circuit must be traversable and must start and end at the same point. Right, now, what we've noticed is that if we have these odd vertices, like we do in this example, we started at one and we ended at the other. We weren't able to get an Euler circuit. It's traversable, but we weren't able to get an Euler circuit. So that's where this 0 comes into play. If you have 0 odd vertices, meaning all the vertices are even, meaning they have an even number of line segments leading them, then you will have an Euler circuit. So if each vertex, oops, that's not how you spell vertex, is even, there is an Euler circuit. And of course I don't have a problem written down, so I will have to find one here. Let's see what the book's got. Okay, so how about this one? And it labels these A, B, C, D, E, F, G, and H. Okay, so we want to know if there is an Euler circuit here, which means what we need to do is count all of the vertices and see if they are even or odd. So A and B, they're both even, right? 2 lines, 2 lines. C has, so if you think about it like a point, has 4, 1, 2, 3, 4. D is 2, E is 2, F is 4, G is 2, and H is 2. So is there an Euler circuit? There is. Yes, there is an Euler circuit. Now, as you go to do this, they're then going to ask you to find an Euler circuit, okay? And when you do this, yours might look different than mine because you might start someplace else, but because they're all even, it means you can start anywhere, okay? You can start anywhere. So let's not be, generic and start with A. Let's start with something like G, okay? So this is how we would show this. We're not just gonna sketch all over this and make a mess. We're gonna write over to the side that we could go from G, and then we could go to C. So G, C, then we might go down to H, and then we might come back up to F. Okay, so far what we've done is we've just gone like that, and like that. Okay. Now from F we could go down to E. From E we go over to D. Then from D we got to go back up to C. From C we'll go up to B. Over to A, finally back down to F, okay? So now we've come down here, we've kind of sketched the whole outer thing. We've come down here, and then the last thing is just to pop us back up to G, right? Pop us back up to G. So there is an Euler circuit, and this happens to be an Euler circuit. So when it asks you to give the path, this is what it wants you to do. Okay, it wants you to say where you start, where do you go next, 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 next. So each step. So that's the showing your work part of this. Now, like I said, you did not have to do this the same way that I did. You could have started anywhere else and gone in a different order, different direction, but as long as all of the vertices are even, you will have an Euler circuit, okay? And you can find it, which is what we did there. Okay. Now, sometimes they ask you to do this problem, but they give you like a room or a house plan, that's what they call it, a house plan problem. And if you have this handout that I put on the calendar, this is just so that I'll try and draw it once here, but my drawings don't look great. So at least you have them right in front of you so that you can see them. But so let's look at a house plan problem. House plan. Okay, so this first example here is a house that has 6 rooms, and each room has a door going through each wall. Okay, so door, 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 door. Okay. Oh, and they labeled it. So again, luckily you have this just right in front of you on that piece of paper. You don't have to draw it every single stupid time. I don't know who decided to label them in this order, but whatever. Okay, so now the question is, can a person go through every door once and only one time? Okay, so can a person traverse each door? So can we go through each door one and only one time? And then we can even take it farther and say, is there an Euler circuit? So can we traverse it, and then can we start and end in the same room? Is there an Euler circuit? Okay. So when you do these kind of problems, it's a different visual than it is over there, but it's really the same idea. So you just have to get into the habit of how this works. So in each one of these, the rooms are the vertices. Okay, so rooms are vertices. The doors are the line segments. And I know that seems kind of weird, but that's what we've got. Each door, each door is a line segment between one room and the other. So, like that. Okay, so we have 6 vertices, okay? And what we need to do is we need to decide whether each vertex, each room, is even or odd. So room A has how many doors? It's got 2, so this would be an even room. But what about room B? Room B has 3 doors, so it's going to be an odd. Room C is an even. Room E has 2 doors, it's an even. Room D has 3, so it's odd. And finally, room F has 2, so it's even. So to this point, what have we learned about this then? Okay, we can be traversable if there are 2 odds. So we have 2 odds, so can we be traversable? Yes. So the answer to this question is yes. Is there an Euler circuit? Can we start in one room, go through all of the doors, and end back in the same room? Okay, so is there an Euler circuit? No, because of these 2 odds. If they were all even, we'd be good to go, but because of these 2 odds, we are not. Which means if we want to show a path, we're going to have to start in one of the odd rooms, and then where are we going to end up after we go through all the doors? We're going to end up back in the other odd room. Now again, you might choose to do this different than I do. Let's say that I decided to start with B. Okay, we're going to start in B, and then I'm going to immediately go down to D. Okay? So we're done that. Okay? Then I'm going to go over to F and up to A. So over to F, up to A. Now I kind of don't have a choice anymore, right? So from A, I've got to go over to B, and then I've already gone through this door, so I've got to go over this way, over to C, down to E, and back over to D. Okay, so come like that. Okay. But traversable in this case means, can you go through every single door? And yes, we did. We started in this room and we ended in that room. Now, were we able to go through every single door and end up back in the same room where we started? No. Okay, but so there's a yes to this one, a no to this one, and here is our path. Okay, and notice how the path ends and starts at different points. So let's look at the other example that they've got there. Actually, you know what, you guys? I hope it's okay. I'm going to erase this and put the other example right there because I want to write something over here in a minute. Okay, so sorry about that. So that other one, give me a moment because it's going to take me a little bit longer. Okay. We've got 3 rooms down below, 1 room up top. We've got door. See, it's so much easier when you have it all done for you. But at least I can erase with my finger. Ay, ay, ay. Doors everywhere. Okay, so door, 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 door. Okay, I'm doing a little bit up here. A, B, D, C, E. Okay, so same question goes. Traversable. And then Euler. Okay, so the way we have to approach this is to really start looking at the vertices. But there is one thing that's misleading here, okay, that they've definitely misled you on. We've got these 5 rooms to our house, right? But you guys see the 6th room? Okay. The 6th room is actually the outside room. Outside. So the 6th room is this whole area all the way around. Okay, and the idea there is this house, which would be kind of sad, but it had no doors to the outside, did it? So there was no outside room in this one because it was completely contained. But as soon as they open up 1 door to the outside, you now have an outside room. So there are actually 6 rooms here, okay? So let's start counting our rooms and seeing about even and odd. Now, lots more things going on here, so let's be sure. So when we start at A, we've got 1, 2, 3, 4, 5. So it is odd. Okay. Same thing with B, right? 1, 2, 3, 4, 5. So there are our 2 odd ones. Now, right off the bat, is there an Euler circuit? No. No Euler circuit because we had some odds at all. Now, if we can just keep those 2 odds, then we can be traversable. So let's start here. So 1, 2, 3, 4. Okay, that's even. 1, 2, 3, 4, 5. There's a 3rd odd. So are we traversable? Nope. Okay. But just to finish it off, just in case, okay, here we've got 1, 2, 3, 4, so this is even. And then the outside room, okay, is the outside room even or odd? So you got to go all the way around. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that guy is also an odd. Okay, so we're out of luck with that one as well. Okay, but so you see, Where someone else might sit here with their pencil and they're sketching all through, trying to see, you guys, you don't have to do that, right? You look at the problem, you count the doors, you go, nope, can't do that one, move on to the next problem, okay? All right. Now, traversable, remember, just have to go through all the doors or all the line segments. In order to be special and have an Euler circuit, you got to start and end at the same point, okay? Now, there's one other one that we're going to look at, and it's called a Hamiltonian cycle. And in a Hamiltonian cycle, we need to pass each vertex once and end where we start. Okay, so a Hamiltonian cycle looks at the vertices instead, and what we have to do is go through each vertex and then end back where we start. So I'm going to go back to our original drawing that we had that looked like this. And this time I'm going to label it. Last time I didn't, so I'll just put some labels on it. C, E, and don't forget this guy is also a vertice, okay? Okay, so we know that this is traversable, but there was no Euler circuit. But now the question is about this Hamiltonian cycle. Now the thing about the Hamiltonian cycle is there's no nice count the evens and odds and see how that one. You just this is a kind of tracer type guy. So, but it has nothing to do with the lines. We do not have to hit every line. So let's say that you started at A. We need to get all the way back to A, but we need to touch everybody else. And in this case, I've kind of set it up nicely. We could go from A to B to C to D to E, up to F, and back down to A. Everybody agree? Okay. Now again, maybe you would have visited F first. You could have gone A, F, B, C, D, E, back to A. Okay. So this one though is just kind of a look and see type problem. But so there is, so yes, Hamiltonian. Now the Hamiltonian guys are also called the salesman problem. Salesman problem. Okay. Now back in the old days, traveling salesmen, they live in one town, they travel around, sell their stuff, and then they have to eventually go home. So the deal was, though, that traveling salesmen apparently weren't the highest quality of people. So normally when they left a town, they left bills unpaid, and they maybe even had girlfriends in each town and that kind of thing. So if you were a salesman, and let's say you lived in town A, you needed to go to all these other towns. But if you ended up back at a town twice, the next time you went back up that town, you're going to get in trouble. You might even end up in jail. So, and if you've ever seen the movie Music Man, you kind of get the idea behind that you go from one town to the next and you kind of want to leave that last town behind you. So that was the idea behind the Hamiltonian cycle. Can you start in one town, visit all the other towns, and then end up back at home? Okay, without going to a town twice and getting yourself into trouble. Now also think about that. If you're doing that, do you have to drive on every road? Okay, did anybody say that you're going to start here and you've got to hit every single road and then end up back at home? No, that would be stupid. Why would you waste your time trying to get down every single road? You only need to hit the vertices or the towns. So the Hamiltonian cycle again is definitely focused on the vertices. Okay, where the Euler circuit is the line segments. Okay, now over here with our two house plan problems, I can ask you the same question about being a Hamiltonian cycle. So I can say Hamiltonian here. Oh, Hamiltonian. So if we go back to this one, this is why I gave you 2 on that handout so that you could write on it and didn't have to erase like I do. Okay, so here, I don't really know why you want to do this. I don't know, you're vacuuming. I don't know. I can't think of a really great example right now, but let's say you start in room D. You want to go through the whole house and you want to end up back in room D, okay? But you don't need to go through all the doors. You just need to go through all of the rooms. So you start at D, cycle your way around. Okay. So yeah, is there a door we didn't hit? Yeah, it really doesn't matter though. Every room we have hit just one time. So we would say yes to the Hamiltonian. And then remember, it will also ask you to write your path. So we could say D, F, A, B, C, E, D. Okay, just go around in a circle on that one. Okay. Now, on this guy, okay, we've got to remember that we have the outside room to start with, or end with, or whatever you want to say. But remember, you can only go outside. You can't go in and out and in and out. Once you're outside, that's your one time outside. So the best way to do this would be to say to start outside. So if we start outside, we could come in through room B, and then we could go into A, over here to E, C, D. Now, can we go back into room B? Okay, no, we can't. But we've gone through all the rooms, so if to make this a Hamiltonian cycle, we just need to end up back outside. So is it possible to start outside, go through all the rooms in this house, and then end back outside? And again, yes, there is a Hamiltonian cycle here. So this guy wasn't traversable, didn't have an Euler circuit, but Hamiltonian, yes. And again, label outside, and then the way I did it was B, A, E, C, D, outside. All right, we're good. Okay, so you might say, you know, what the heck, who cares about these types of things? And, you know, some of them are useful, some of them are not. Again, this idea of planning a trip and wanting to hit all the different towns and then end up back at home with kind of like the, you know, not having to go through every single road and everything. So the Hamiltonian, that is a helpful one. Definitely. Where do the Euler circuits come into play though? So here's where the Euler circuits happen. Euler circuits are used in grocery stores, in parking lots, in subdivisions, okay? So the idea behind the Euler circuit is, like if you're in a grocery store and you're doing a full, thorough grocery shopping, okay, not just going in for one thing, but you have to fill your whole house. The idea behind that is you would like to go into the grocery store, go up and down each aisle, up and down and up and down, and then eventually come back out to the front and go pay and go out the grocery store. But what you don't want to do is have to retrace your step down aisles you've already been to. So you want to go up and down the aisles, and then at the end, you don't want to end up back in the far back corner, you want to end up back at the front. So a grocery store that has an Euler circuit is a grocery store that works well. And we've all been in grocery stores that work well, where you go in the grocery store, you go up and down the aisles, you get back to the front, and you're like, oh, I hit everything, I'm good to go. But we've also been into grocery stores where you go in, you start going up and down the aisles, and then they might even have some aisles this way, and then they have like a couple like outer bumps and all sorts of different things. Okay, well, by the time you end up finishing, you end up and you look at your list and you're like, well, crap, I've missed the milk and I missed the eggs and I missed the bread. Because what's happening is the circuit that there is no circuit that they have created. So in order to go through the whole store, you have to actually recross your path. So if you don't want to recross a path, there's no way you can get back out the store. So, and what happens is you end up missing a couple aisles. You get back to the front and you go, oh, how did I miss that? It's because it wasn't set up well. Now, like I said, parking lots as well, and especially like a parking structure. A parking structure is definitely set up with an Euler circuit in mind. You come in, actually, you know what? Parking structure could even be traversable, right? Because you come in one way and you go out the other. So that idea of starting and ending at the same point, you don't even need, we could be just traversable. But the idea is that you go into the parking structure. You go through each aisle in the parking structure as you go up and up and up, and you drive through each aisle in the hopes of finding a parking spot, right? And then you cycle your way back down, okay? And by the time you get back out or to pay, if you have decided to go through the whole parking structure, you have not ever crossed your path, unless you chose to, but you've not ever crossed your path, and you're able to head out. If it wasn't traversable, that would mean that you would have to back up someplace. So have you ever been in a parking lot where you park someplace and then you go to leave and all of a sudden you're like, what the heck, this is a dead end. And so you have to do like the 3-point turn and turn around and head out. And I'll tell you what place has a lot of parking lots like this is Cal Poly. Cal Poly has a number of parking lots where you turn one way into the parking lot and all of a sudden you're at a dead end. And if the parking lot's full, it's a real pain in the butt to get out of. Those parking lots are not set up with an Euler circuit in mind. Funny that Cal Poly, of all places, they didn't take into account Euler circuits and Hamiltonian cycles. But it's really interesting, and now that you have an understanding, you kind of know what this is, the next time you go to some place like a department store or a grocery store, or you're driving in a parking lot, and all of a sudden you hit that dead end and you go, oh my gosh, this isn't traversable. Where it never had meaning before, all of a sudden you're gonna start to look at it and go, oh my gosh, I see it now. So this idea of Euler circuits and Hamiltonian cycles definitely comes into play in city planning, okay? City planning, or again, like building planning. It's important that you make a nice flow. That's what we're looking at here. And there's actually math behind it. And luckily the math isn't that bad, okay? So have some fun, drawing some shapes and trying to traverse them and see if they have an Euler circuit or a Hamiltonian cycle, but that's all we're doing in this lecture, okay? So like I said, went from logic to something a little bit more on the fun side, okay? All right, guys, have a wonderful day. I will see you next time.